Hi, and welcome to the premiere episode of Focused on Physics. This new video series was created to provide my take on various math, science, and engineering topics. If you have a specific question or topic you'd like to see in a future video, please let me know in the comments. Your feedback will help drive and build this series. In this episode, we will practice using the kinematic equations for one-dimensional motion with constant acceleration. Mastery at this level will set us up for two-dimensional motion, often called projectile motion. Let's get started. Here are the 5 kinematic equations. You may be wondering why I'm showing 5 equations when your teacher and textbook likely only presented 4. Most courses tend to omit the first equation shown in this table. It only takes a few algebraic steps to derive it from the other 4. The kinematic equations shown here accurately describe an object's motion in all cases that assume constant acceleration. This assumption of non-changing acceleration is key. Acceleration can be positive, negative, or even zero, but these equations are only valid for the portion of motion in which acceleration does not change. It is possible to accurately describe motion where acceleration isn't constant, but we will save that topic for a different video. Much like there are 5 kinematic equations, there are 5 kinematic variables: initial velocity, final velocity, acceleration, displacement, and time. Each equation utilizes only 4 of these variables. This table is designed to emphasize which variable is missing in each equation. This will be very handy for solving 1- and 2-dimensional motion. Let's demonstrate that now. Example 1. If a rifle fires a bullet straight up with a muzzle speed of 300 meters per second, how high will the bullet rise? Ignore air resistance. When solving these types of questions, I like to start by setting up this table. The first step is to populate the table with the things that we know. So, what do we know? The bullet leaves the rifle at a speed of 300 meters per second. We need to decide which direction we consider to be positive. I prefer to let up be the positive direction. This means the initial velocity v0 is positive 300 meters per second. That is all the information the problem gives us, but we can deduce more. For example, we can assume the rifle was fired on the Earth's surface, where we know the acceleration due to gravity is 9.8 meters per second squared toward the Earth's center. So let's update the table with our assumptions. We've already said that acceleration would be 9.8 meters per second squared downward, so let's write that down. Notice the negative sign on the acceleration? We need it there because the Earth's center is opposite the bullet's initial velocity, which we chose to be positive. Now, let's talk about the final velocity. When we say final velocity, we don't mean the speed of the bullet after it's fallen back to the Earth. We really mean, what is the velocity of the bullet at the end of the portion of motion that I am analyzing? That last part is key. We are not analyzing the entire path of the bullet's motion. We are only concerning ourselves with part of the bullet's motion. The part from exiting the rifle to reaching its maximum height. Let's visualize this situation. Here we have a ball. In just a moment, we will toss the ball up and watch it come down. 4 physical parameters are represented on the screen: velocity in red, displacement in blue, acceleration in yellow, and time in white. The size of each arrow represents the magnitude of the quantity it represents. Initially, the red velocity arrow, or vector, is quite long, while the blue displacement vector is 0. Now, let's start the timer. The ball moves upwards, which increases the displacement vector. As the ball gains height, it loses speed until freeze. The ball reaches maximum displacement. Let's analyze this snapshot in time here. The acceleration vector has not changed thanks to the constant acceleration requirement. But what about the velocity vector? It has dropped down to 0. This happens because the acceleration vector points downward, and so eats away at the velocity vector. We see that when an object is tossed into the air, the vertical velocity is 0 at maximum vertical displacement. Let's see what happens when we unfreeze. On its way back down, the ball gains speed. However, its velocity is now negative. Once the ball hits its initial starting point, the velocity vector has the same magnitude or speed that it started with, but the vector is pointing in the opposite direction. The 0 value for displacement is a result of the ball ending at the same place it started. Again, the acceleration vector has not changed. From this discussion, we conclude that the bullet reaches its maximum height at the brief instant when it stops moving upwards and begins moving downwards. That is, when its final velocity is 0. Let's update our table. At this point, we have 3 of the 5 kinematic variables. Recall that each kinematic equation only needed 4 of the variables, which means we have enough information to determine the remaining 2 unknowns. But for which one are we solving? Some problems might ask for both, but in this case, we only need to know one: how high the bullet traveled, or its displacement. I like to put question marks in the table to remind myself what I am calculating. This will be a very useful reminder for more complicated questions. I also like to cross out any variables I could ignore. Once the table is filled in, we need to determine which of the 5 kinematic equations we can use to solve the problem. We have already determined that we are looking for displacement and that time is unnecessary. We should therefore select the equation that doesn't require time but does have displacement. Looking down the time column in the equations list, we see that every equation needs time but the last equation. Let's write it down. At this point, the physics is done and all that is left is algebra. I've highlighted displacement in yellow. To rearrange the equation, first we subtract the square of the initial velocity to the other side. Next, we divide by twice the acceleration. The equation is rearranged, but let's move displacement to the other side. Now we will substitute the values from our table into our equation. We are ready to solve. First, we will drop 0 squared and multiply 2 by negative 9.8. Make sure you keep track of the negative signs when working through the algebra. Even seasoned physics students forget about them. If your final answer doesn't seem to make sense, double-checking your signs is a good place to start troubleshooting. Notice that the negative signs cancel out. This is reassuring because the bullet is traveling upwards. The direction we chose is positive. Next, we will square 300 meters per second, which gives us 90,000 meters squared per second squared. A common mistake is to forget to square the units as well. Let's break up the fraction into numbers and units. The units are written as the division between 2 fractions, and we should treat them like that. We keep the numerator and flip the denominator. Meters squared cancels with meters to leave meters, and seconds squared cancels outright with seconds squared. The final units are meters, which is what we would expect for displacement. Plugging 90,000 divided by 19.6 into our calculator gives 4,591.84 meters. The units are appropriate for displacement, but that number, 4,591.84, is very specific. It is fair to assume that Earth's gravity is well known and doesn't add much uncertainty into our calculation. However, how much faith do you really have in that bullet's initial velocity? It doesn't make sense for us to conclude a number so specific when our underlying variables aren't very certain. So while our calculator tells us 4,591.84, it makes more sense to say the bullet will rise about 4,600 meters. Finally, we should answer the question in English and check that our result actually answers the question being asked. That was a good introductory problem. Let's take a look at a question that's a bit more complicated. Example 2. In a classroom demonstration, a glider moves along an inclined air track with constant acceleration a. It is projected from the start of the track x equals 5 with an initial velocity v0. At time t equals 8 seconds, it is at x equals 105 centimeters and is moving along the track at velocity v equals negative 15 centimeters per second. Find the initial speed v0 and the acceleration a. If you're feeling confident, pause the video here and see if you can solve this problem on your own. The first step with these kinematic equations, just like before, is to organize our variables into a table. We are concerning ourselves with the glider's motion from x equals 5 to x equals 105. The total displacement of the glider is the difference, or 100 centimeters. The glider took 8 seconds to travel this 100 centimeters and was moving at a velocity of negative 15 centimeters per second. Let's write this down. This problem is straightforward in letting us know what we need to calculate. Just like before, we can indicate our goal by using question marks. With our table filled, we now turn back to the kinematic equations. Just like before, we have 2 unknowns. This time, however, we need to calculate both. We can only do one at a time, so let's forget about acceleration for now and focus on the initial velocity. We need to choose the equation that doesn't include acceleration. Scanning the list, we see the third equation is what we need. If you did this problem on your own, you might have gone a different route and used the first equation in the list to solve for acceleration first. The math will work out the same either way, so keep watching to see how you did. Now that we've chosen our equation, let's write it down. We need to solve for the initial velocity. First, let's clear out the 1/2 by multiplying by 2. Next, divide by time. Now we can clear out the parentheses and subtract the final velocity over. Let's move initial velocity over to the other side. Now we can plug in our numbers. 2 times 100 centimeters is 200 centimeters, and 2 negatives make a positive. 200 centimeters divided by 8 seconds gives 25 centimeters per second. Finally, 25 plus 15 gives an initial velocity of 40 centimeters per second. So, how did you do on your own? Let me know in the comments. Remember, we need to solve for both missing quantities. We can fill our result for initial velocity into the table and continue forward. Let's remind ourselves of the kinematic equations. We are looking for acceleration, so we should choose an equation that has it. This time around, we have 4 equations from which to choose. Any of these 4 equations will give us the correct answer, so which do we choose? Personally, I would like to avoid squaring numbers if I don't have to, so let's choose equation number 4. The first step to solving for acceleration is to write down our equation. Next, we will subtract initial velocity to the other side. Now we can divide by the elapsed time. Once more, we will move our solve variable over to the left. Let's plug in the numbers, keeping track of our negative signs. Negative 15 minus 40 is negative 55 centimeters per second. Just like before, let's break our division problem into numbers and units. It may be tempting to cancel out the seconds, but don't do it. We are solving for acceleration, which has units of centimeters per second squared. Finally, negative 55 over 8 is negative 6.875, which we will round to negative 6.9 centimeters per second squared. Answering the question in English, we have solved the problem. So, how'd you do? Let me know in the comments below. Thanks for watching Focused on Physics. If you enjoyed this video, subscribe and hit that notification bell so you'll always be the first to learn about our latest content. Be sure to give this video a thumbs up as well. See you next time.